Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A, Paper 3 from June 2022. Okay, so these questions are from different areas of chemistry. Ammonia, NH3, and the ammonium nitrate, NH4NO3, are compounds of nitrogen. The boiling point of NH3 is minus 33. The boiling point of NH4NO3 is 210 degrees. Explain why there is a large difference in the boiling points. So number one is to say what each of these things are. So we've got NH3 here. That is just a simple molecule. But if you compare it to NH4NO3, that's NH4 plus and NO3 minus. Those are oppositely charged, so it's ionic. All right. So that means the reason is that NH3 is a simple molecule and has hydrogen bonds and London forces. These are weaker intermolecular forces compared to NH4NO3, which has ionic bonding. And this ionic bonding requires more energy to overcome. They are stronger than the IM forces, or the intermolecular forces. You write the whole thing. I get to say IM because I'm lazy. So two students discuss the oxidation numbers in ammonium nitrate. One student claims that the two nitrogen atoms have the same oxidation number. The other student disagrees and claims that the nitrogen atoms have different oxidation numbers. So explain with reasons which student is correct. So if we look at NH4 plus and then the NO3 minus, the oxidation states of this. So if we look here, we have +4 because each one of them is +1, and that makes a +1 overall, so it's got to be -3. So here, its oxidation number has got to be -3. And then over here, we've got, 3 lots of -2, -6, so +5. So then its oxidation number is +5. So then the other student is correct. Which one said that they're different? So the other student. Now it says brass is an alloy of copper and zinc. The mass spectrum of a sample of brass is shown below. The peaks at MZ63 and 65 are from the Cu63 Cu and 65 Cu isotopes of copper. The remaining 4 peaks are from zinc. So what are the percentage compositions of copper and zinc in the entire thing? So if we have a look, so 63 and 64 are from 63 and 65, sorry, are from the copper. Fine. So that means that those two added must be the percentage composition entirely of the sample that they took. So 45 plus 64 plus 20.36 gives us the percentage of copper of 66%. And then for the rest of them, 16.82 plus 9.53 plus 1.38 plus 6.27 should give you 34%, because all of those came up from the sample of brass, so it must have all been in there. Now it says calculate the relative atomic mass of the zinc in the sample of brass. So the relative atomic mass of the zinc would be, so your mass of your isotope equals each abundance times its MZ over the total abundance. Now, because we're only looking at zinc, we only need to deal with the zinc's ones. So zinc's abundances are 16.82% times 64 plus 9.53% times 66 plus 1.3867 plus 6.2768. And then we need to divide it over their total abundance, which is 34%, not 100, because they're not, it's only, all of the zinc in this only makes 34%. If you do that, it gives you an answer of 65.42. So now it says the structure of an organic compound is shown below. The protons are in 4 different environments labeled 1 to 4. What are their splitting patterns? So if you look at this first one, it's a CH3. So its splitting pattern here has to be, well, next to it is a CH2. So N+1 rule, it's going to be a triplet. If you look at carbon 2, so if we look here, there's none here. However, there's 3 there. So its splitting pattern is going to be a quartet. Next, if we look at carbon number 3, so in a carbon number 3, it's got none here, but 1 here, so it's going to be a doublet because that 1 there causes it to split, because 1 plus 2, right? And then if we look at carbon number 4, it's attached to this carbon, which is attached to a carbon with 2 on it, so it's a triplet. So the table shows the chemical shifts of the peaks in the proton NMR spectrum of proton environments 2 and 3. So just where the peaks of 2 and 3 have the chemical shifts which are shown in the table. So if we look at environment 2, that's what CH2 next to a C. So CH2 next to a C double bond O. And it says, why do they show those chemical shifts? So it must be something to do with the data sheet, CH2 to CH2S. So if we look at the data sheet, it gives you that peak. So the environment 2 is that your protons are on the carbon adjacent to C double bond O, because if you look at the data sheet, that's what it shows here. Whoops, that's massive, but there. It's at 2.5. It's talking about this carbon here. So it's explaining how do you know that that's why it's there, and it's because of that. So then the other environment 3 is at what, 3.6? So the 3.6 is going to be what? Let's have a look at the environment of the third one. Sorry. So this one's here. So it's here, and it's also there. You can't just look at the data sheet and say, oh, 3.6, because if you look at the data sheet, it says this, and that's not what that is. So the only other explanation for why it's got this chemical shift as shown in the table is probably because it's in between an aldehyde and a ketone. So the protons are surrounded by a C double bond O on either side, you could probably say, to be honest, either side. So now it shows this, and it says glycine H whatever is an alpha amino acid. It reacts with this to form this. Glycine reacts with that to form that. The salts are derivative, blah 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 blah. State the different bond angles and why they're different. Well, whatever, fine, right? Okay, so let's have a look here then. So the salt of the H2NCH2COONA plus. We need to look at which part of it. We need to look at the actual stem of the carbon. So every single amino acid in the world looks like this, and then this, and then it's this, and then it's gone R group, and it's asking about the the H-NH bond angle. So it doesn't give a dang about all the rest of it. All it's looking at is here. So if we look here at this N, it's got it's next to a carbon. It's got 3 bonding pairs, 1 lone pair, so it's going to be 107 degrees. Whereas if you look at here, you can see it's NH3Cl. So one of those has gone to a Cl now. So it's 4 bonding pairs, 4 lone pairs, because even if it is a data covalent bond, you consider it a singular pair. So that's 109.5 degrees. So then your reasoning is exactly what I just said there. So 107 degrees for the top one because 3 bonding, 1 lone pair. And then for the other one, it's 109.5 because it's 4 bonding pairs, 0 lone pairs. Glycine reacts with aqueous copper-2 ethanoate to form copper-2 glycinate. Copper-2 glycinate is a complex which exists as 2 square planar isomers. Write an equation for this reaction and draw the structure of the 2 square planar isomers. So it's told you in the question what half the equation's going to be. Like if I just draw an arrow like this, we can figure out the rest, right? So it's told you that glycine reacts with copper-2 ethanoate. So copper-2 ethanoate is going to be Cu and then CH3COO minus, and 2 of them, like that. And they've told you it's reacting with glycine, so there's going to be 2 lots of the, and it's also showing you here as well, 2H2NCH2COO, right? The reason we know it's copper ethanoate copper-2 like this is because that's a salt, copper ethanoate, it's a copper ethanoate ion. It gives you that. So then, adding those together, you will like, well, it's told you this in the question that it's made that. So it's H2NCH2COO2. And then it's going to make whatever's left behind. So those 2 ethanoates come out. So it's 2CH3COOH, like that. Next, it says next it tells you its structure. So it's told you that it makes square planar structures. So I just start by drawing out the copper in the middle, and then I'll draw my dotted arrows and then fill in the rest. So my dotted dashed arrows, or whatever you want to call it. So we need to find out which part of this is actually doing the lone pairage here. So there's going to be a lone pair here, and there's going to be a lone pair there as well. So the oxygen is going to be one of them, and then the NH2 is going to be the other as well. So I've got a lone pair there, not the double bond oxygen, the single bond one. So you've got that, and then we have our double bond O on that carbon, and then it's connected to what? Another CH2, and then it's connected to a CH2, and then that's connected to an NH2 like that. That looks absolutely disgusting, but yeah. And then we've got the other O here, lone pair, then a double bond O like this, and then a H2C here, and then an NH2 there, and like that. Sorry, that's really badly drawn. Let me tidy that up a bit. Here, and then we've got like a bond there. And that adds up. So I usually draw it lone pair by lone pair. So that's one of them. Now the other one is that's where these are kind of like on the same side. So now I'm going to do the same, but just flip one of them around, and that'll be the other one. So then the NH2 goes here. There's my lone pairs. There's my C double bond O. There's my CH2. There's this. And then I'm going to put my NH2 here. There's my O there. That's going to be my C with its double bond O there. That's going to be my CH2 here. I shall do H2C here, and then that. That's the other one. Done. So this question's about redox titrations. Calcium hypochlorite is an ionic compound used in bleaching powder. The ClO- ion and CaClO2 is the active ingredient that kills bacteria. So calcium hypochlorite is prepared by reacting chlorine gas with calcium hydroxide. And we've got this equation here, 2Cl2 plus 2CaOH2 plus goes to CaClO2 and then CaCl2 and 2H2O. 420 decimeters cubed of chlorine measured at room temperature is measured with an excess of CaOH2. The solid products are dissolved in water to give you a 4 meter cubed solution. Calculate the concentration of CaClO2 aqueous in the solution in moles per decimeter cubed and give your answer to an appropriate number of significant figures and in standard form. Because it's told us that we have 420 decimeters cubed of chlorine at room temperature, we can use moles equals volume over 24 decimeters cubed because they've told us it's at room temperature and pressure. So the moles of Cl2 is going to equal 420 divided by 24, which is 17.5 moles. Now, don't just blindly work out moles. Think about what you're actually going to do with them. So we've got this. We've got our reaction equation here. That means that 175 moles of this will react with how much CaCl2? Half of that. So the moles of, well, not react with, react to produce half of that, sorry. So the CaClO2 is going to equal half of that answer, which is going to be 8.75 moles, right? Now they want the concentration of that solution made. So they've given you 4 meters cubed. The way I like to think of it is if you're going from 1 meter to a decimeter, what you would do is you would divide it by 10. So if you're going from 1 meter squared to 1 decimeter squared, you're going to divide by 10 squared. And if it's 1 decimeter cubed to 1 meter cubed to 1 decimeter cubed, it's going to be divided by 10 cubed. So that means to get from 4 meters cubed to that, we're going to divide it by 10 cubed. Or divide by 1,000. So if we do that, we get our volume, we get whatever volume that ends up being. So then the concentration is going to be 8.75 over 4 divided by 10 to the 3. If we do that, we get 2.19 times 10 to the minus 3 if we keep it to 3 significant figures. So now it says calcium hypochlorite is heated and it decomposes to form CaCl2 and CaClO3, and this is a disproportionation reaction. Write an equation for the decomposition, explain using oxidation numbers why this is the case. So they've told you nearly the entire equation itself. So we've got CaClO and then a 2 here, and they've told you it decomposes into CaCl2. So you definitely know that these two are going to be on the either side. You can fill in the reactants any other way, like after, but this is pretty much it, to be honest. Then we need to balance it. So we've got 6 oxygens here, whereas we've got 2 here. So I'm going to put a 3 there. That gives me 3 calciums, but we've got 2 calciums here. I've already balanced out the oxygens, and I've got, 3 chlorines now. So what could I do? Well, we've not got 3 chlorines. We've got 3 times 2 chlorines, so that's 6 chlorines. So I can put a 2 here, and that should be fine. Done. Now, for the explanation, this ClO, we've got 2 of them. So this ClO minus ion must have a charge of -1 overall. So we've got -2, so that chlorine must be a +1. So chlorine goes from +1 to, and then let's have a look what's going on. So in here, CaCl2, it has become -1. So -1, but also, what about in this CaClO3 bit here? So the ClO3, if there's 2 of them, that's going to be a -1 overall as well. So that's -6. So that has to be +5 as an oxidation state. So it also goes from +1 to +5. But that doesn't tell them that it's a disproportionation reaction, because you need to say what's being reduced or oxidized. So therefore, here, because it's oxidation number, how much it's been oxidized, that's what the oxidation number is it's got to be reduced because it's getting less oxidized, more reduced. It's going down. Remember oil rig and all that. So then if it goes from +1 to +5, its oxidation number is going higher, meaning it's becoming oxidized. So oxidation. And there you go. So a student analyzes the redox reactions shown below. State symbols have been omitted. The student concludes that different ions containing chromium can act as oxidizing and reducing agents. Using the term oxidizing agent, reducing agent, and ideas about electrode potential and equilibria explain how this student is correct. So this person is saying that different ions with chromium can act as oxidizing and reducing agents. So before I even delve into this, I know that the ions I'm going to be dealing with is Cr3+, which can eventually, in some way, shape, or form, become Cr2O72-. Now you can see that here, that's +6. So if we're going this way, that means it's being oxidized. The other way is Cr2O72-. That's oxidized, Cr2O72-, blah, 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 plus the certain number of 6 electrons, or however many it is, can eventually become Cr3+, so that one is reduced. Now, whenever you oxidize one thing, something else has to be reduced. If this is getting oxidized, something else is reduced, so this is actually a reducing agent. The Cr3+ can act as that. And then here, again, because whenever you oxidize something, something else has to be reduced and so forth. If this is reduced, something else has to be oxidized, so this is an oxidizing agent. So now you know what directions to go for. You can just pick now. So let's choose an we'll do the reducing agent first. So in terms of reducing agent, we need to make sure we start with CR3 plus and eventually finish with this. So in that case, we look at where our CR3 pluses is and we see it's here and we want it to go that way because we want it to oxidize. So if we want it to oxidize, if we look at these B potentials, we need it to be the more negative one out of both of them. So if we set that to be an oxidized, the other one that's reduced has to have a higher potential, which would be this one. Remember that in a reducing agent itself becomes oxidized. So that means Cr3 plus can reduce. And remember, if one thing's getting oxidized, you're going to give out electrons here, lose them. So the other one's going to take them in. So what's being reduced is the FeO42 minus. So if we were to combine these equations, all you do is you just times that by 2 and put them together and then remove the electrons. So we're going to have 2Cr3 plus 7H2O plus, because we're going that way, and then we're going to add this stuff in. So plus two lots of them, O42 minus plus 16H plus goes to, and then Cr2O72 minus plus 14H plus Fe3 plus, well, 2 of them plus 8H2O. And then we need to tidy this up. So these all cancel out. We're left with 1H2O there. And then we've got, 2H pluses here and that. So then if we tidy all of this up, we get 2Cr3 plus 2H plus 2 FeO42 minus goes to Cl2O72 minus plus H2O plus 2 Fe3 plus. So then we need to, so we've talked about oxidizing, we talked about reducing agents, we need to describe about the ideas of electric potentials and equilibrium and explain how they're correct. So then we need to say, well, the E cell for the Cr3 plus is more negative than the FeO42 minus, therefore it's oxidized, and FeO4 minus is reduced. And you need to say why. It's because the Cr3 plus equilibrium shifts that way. It's going in that direction, so shifts to the left. So now we've talked about that first one. Now we look at our oxidizing agent. So remember that an oxidizing agent makes something else get oxidized and it itself becomes reduced. So because we scribbled it out up here, we know that we're going to have to go from the Cr2O7 to Cr3 plus. So again, this is our equation of choice. If we want that to be reduced, then the other thing has to be oxidized. So it has to have a lower EMF than the other one, so the E cell. So that would be here, because that's more negative. So in the oxidizing agent, it's the same thing as well as before. So Cr2O72 minus can oxidize C2H5OH. And then the same thing happens here. So because we're reducing this, it will go this way. Because it's gaining those electrons, this will become oxidized to go the other way. So just to save the time, I'm just going to quickly scribble down what the equation is. So again, you would times that by 3 and then combine them. So if we do that, we get Cr2O72 minus plus 8H plus 3C2H5OH goes to 2Cr3 plus 7H2O plus 3CH3CH. And the reason is that the E for the Cr2O72 minus is greater than the E cell for the C2H5OH. Therefore, the Cr2O72 minus is reduced and the C2H5OH oxidized. So its equilibrium is to the right, the equilibrium for Cr2O72 minus, that is. And that's how you do it. That's whenever we're doing this stuff with redox potentials, we're actually shifting equilibrium when we're doing that oxidation reduce thing. So now it says, a student bubbles hydrogen sulfide gas through an acidified solution containing manganate ions. A redox reaction takes place and you get aqueous manganese ions, a yellow precipitate, and one other product. Construct an equation. So again, when you're doing this, just think about what they've already told you in the question and what can definitely come up. So they've told you that there's hydrogen gas with manganate ions. So we know that definitely in this equation on the left, it's going to say H2S and MnO4 minus, no matter what. All the other bits and bobs we haven't figured out yet, we can work that out. So then, we know this then becomes manganese ions, so Mn2 plus, and then some of the mysterious stuff as well. So look at what's in these equations. Because it's a redox equation, we need to have a look at what's happening to oxidation states. So the oxidation state here of manganese is +2, but if we look at the bit before, it's going to be -8. So -8 for these two, because it's -2 for each of those, it's got to be +7. So if it's +7 and it's become +2, what's happened? It has gained 5 electrons. Its oxidation number is dropped by 5. If that's the case, this is redox, so something in here will have lost a certain number of electrons. So in this case, what we have here is we've got 5H2S, so that's going to be +1 for each of them, so it's going to be +2, and the overall thing is 0, so that's going to be -2, right? So if the only thing we can really do is, if that's gaining electrons, this has probably lost some. So if it's probably lost some, and it's been reduced, then it's probably made something with an oxidation state of 0. So it's probably made sulfur, which is a yellow, like solidy stuff. So that's an oxidation state of 0. Now, if this wants 5 electrons and this can only give away 2, is we need to balance this to, make them have the right amount. So what I can do is if I do 5 lots of this, that means we've lost 10 electrons in overall. Because remember, each time we lose, each one of these loses 2 electrons. And then if I times that by 2, then because each of these gain 5, now it's gained 10 and we're happy. So then I times that out, right? Next, what I do is because I balance out all of my elements, so we leave water and oxygens and stuff like that to the end. So we've got 2 MNs here, 2 MNs here. I'm quite happy with that. And then if we look, we've got 5 S's here, so we're going to put a 5S there as well. So 5S there. And then we need to balance the oxygen. So we've got 4 oxygens here, but there's 2 of them. So remember, that's 8 oxygens. So we're going to add 8 H2O. And then we need to add the right amount of H pluses. So in this case, there's 16 H's on this side, but we already have 5 times 2, that's 10. So in that case, we're going to add 6 H pluses here. And there you go. And that, when a question asks you what the conditions are running, because there's an H plus here, it's acidic. And that's what it tells you there as well. So even more hints as well. But that's how you do these questions, is you've got to look at the order I always follow with these is look at the electrons that have been exchanged, balance them out based on the electrons they've been exchanged, balance any element that is an oxygen or hydrogen, then to balance oxygens you add water, and then you finish with the hydrogens. Don't do it the other way around where you get all the H plus and then finally add electrons. Personally, I think that's just not the best way around it, and you'll probably get it wrong because it doesn't test your knowledge and actually appreciate that this is being reduced and that's being oxidized. So it says information about 1-bromobutane, butane 1 shown in this table. So what do we see here? We've got a lower melting point for 1-bromobutane, a lower boiling point, and a higher density. A student prepared a sample of 1-bromobutane by refluxing this much butanol with sodium bromide and sulfuric acid. After the reaction, it's purified, and they get this much pure bromobutane. So it says draw a diagram to show how the student would have carried out the reflux and draw a percentage yield of the 1-bromobutane that they obtain. Describe how they could have obtained 1-bromobutane after the mixture obtained after reflux. So, I'm just going to do it here out the way. So we've got a beaker chilling it with our reactant, so a round bottom flask, and then we've got our beaker with water, and then we've got heat. And then connected to it is going to be a little bung there, and then a Liebig condenser as well. And then remember, water comes in at the bottom, and then it comes out at the top, so it doesn't pool. We want to make sure the water's forcibly going that way, otherwise it'll just pool at the bottom and build up like that, and that's not a very good way of cooling. And then in here are your reactants. Right. So it takes just a second to realize what they're doing here. So they've got a halo alkane, and then we have an alcohol here. So what's going on is we've got 1, 2, 3, 4, that is butan 1-ol, and then they switch it to 1, 2, 3, 4, and they've now got a Br here instead. So you should be able to recognize straight off the bat that's nucleophilic substitution, and all you're doing is swapping that and that. So that means they're going to be in a 1-to-1 ratio anyway, because they're only swapping one group for one thing. So we've drawn the diagram, cool. Now we need to calculate the percentage yield that they obtain. So now what we need to do is we need to look at what they've actually reacted and find out the theoretical amount we should make, and then we can figure out the percentage yield. So in the question they've told us we have this much butan 1-ol. So that means the moles of the butan 1-ol is going to equal 9.25 over, because that's its mass, over its MR, which is 74. That gives us 0.125 moles. That's how many moles of that we get. Now, we know that they react in a 1-to-1 ratio just because we're swapping them as above. So that means that your moles of your 1-bromobutane is also going to be 0.125 moles. So its mass is going to equal moles times its MR, which is going to equal 0.125 times the MR of the bromobutane, which is 136.9. So if we do that, we get 17.1125 grams. Now, the percentage yield equals your actual over what you should theoretically get times 100. So in that case, the actual amount they got was 6.10 centimeters cubed of that, right? So you're like, oh my God, I don't know the mass. Don't worry, don't get scared. It's telling you the density in grams per centimeter cubed. So we need to find out what our actual yield is. So our actual is going to be, well, they've told you its volume, that's its density in grams per centimeters cubed. So all you do is you do 1.268 times 6.10, because density equals mass over volume, but you can also work it out from the units, 1.268, and that gives you 7.7348. Therefore, their percentage yield is 7.734 divided by 17.1125 times 100 over 17.1125 times 100, which gives you a percentage yield of 45.2%. Now it says, describe how the student would have obtained the pure 1-bromobutane from the reaction above. So what we're doing is we're separating liquids. So if we're separating liquids, we don't use a Buchner flask and all that. What we're going to use is we're going to use a separating funnel. So what you do is you put a separating funnel and you need to decide where the organic layer is. So the organic layer is either on the top or the bottom, depending on its density. Now this is more dense, meaning it's going to sink to the bottom. If I put a block of metal in water, it sinks to the bottom because it's more dense. So it's not always the top layer. Some people are like, oh my God, it's the top layer, bro. It's not. You can see that it's more dense here. So they always do that. They always love throwing you off there. So the separating funnel, the organic layer we want is more dense, so it's on the bottom. So all you do is you open the tap and remove, open tap, remove bottom layer in flask, discard the top. And then what you need to do is we need to remove any aqueous stuff in it. So what you do is you dry with like anhydrous CaCl2, or you could use MgSO4. And then what you want to do is, because you want to really purify it, you want to then, once you've dried it, you want to redistill as well. But we need to figure out at what temperature. So it boils at 102, it melts at this, and this is 118. So what we want to do is we want to redistill at temperature where it boils. So at 102 degrees Celsius, and then you can recondense it and so forth, and you'll get pure stuff. That's how you do it. So whenever you're separating liquids in organic chemistry, you need to use a separating funnel, but you need to factor in its densities, and you might need to use distillation as well. Whereas if it's a purifying like a crystal thing, like a solid thing, then you're going to have to use like a Buchner flask and, crystallization, recrystallization and all that stuff. So now it says butane 1 reacts with sodium bromide and sulfuric acid to form 1-bromobutane via nucleophilic substitution, and the mechanism takes place in 2 steps. The oxygen atom of the alcohol group accepts a proton to form a positively charged intermediate, and then bromide ions react with the intermediate from step 1 via nucleophilic substitution to form 1-bromobutane. So they love doing this, where they give you a mechanism you don't recognize, and then people panic, being like, oh my God, I don't know this mechanism. Oh! Like, just work with what the question's telling you. So a good start is to draw each thing. So I'm going to start by drawing the butane 1-ol, because that's what it's starting with. It says in the question, C3H7, and it's a carbon, and then there's an O and an H, right? Then what do we have? We've got the H's and the H's here. So the first step says the oxygen atom of this alcohol group accepts a proton to form a positively charged intermediate. So remember that this has a lone pair on it as well. So it's going to accept a proton. So by accepting a proton, it's bonding with the proton. Remember, protons are H+, so they don't have any electrons to give. So this lone pair goes here like that. That's the curly arrow showing the electrons here are being given to the H+, and that means a bond has now formed with it. So the intermediate is going to be the same thing, just with that O on it, but remember that we're going to have, well, I'll get to it, O, and then like an H2, and there's going to be a plus. The reason is because every covalent bond is one pair of electrons, one from each thing. This one hasn't had an electron from the H+. It's actually given both of them away, so that plus has now been attached onto here as well, and that's why we get that. So that's your intermediate. Step 2 then says bromide ions react with this intermediate from step 1 and produce via nucleophilic substitution to give you this thing. Fine. So draw out the steps first that you know you definitely have got going on. So I know for a fact that, I'm going to just write the H's out like this, we have this intermediate from before. And they've told us that bromide ions are going to react. We need to figure out whether bromide ions react. So the mechanisms that you're familiar with, let me just move this bromide out of the way, actually, just so it's a bit nicer. Br minus, and there's my lone pair. Usually these go for something that's electron deficient. So generally it's the carbon, because this carbon, remember that this oxygen is still more electronegative, so it's going to have a slight positive charge here and a slight negative charge here. So because this is a nucleophile because of its lone pairs, it wants to go for something that is deficient in electrons. So what it'll do is it'll donate its electrons like this. Right now carbon's not happy. Carbon's like, yo, I got too many bonds. 1, 2, 3, 4, 5. I need to boot something off. So the way I like to think of it, well, it's not going to boot that off or this, because the electronegativities of CNH are presumed to be the same. Whereas here, the electrons in this carbon-oxygen bond are really close to here, and that final push of these electrons coming in will repel those onto there like that. So that's exactly what I do. This bond here would break, and its electrons goes to that oxygen there. So as a result, you then end up with C3H5CHBrH plus, and then you're going to make H2O as well because of the other H's and stuff being mucked about with here, but this is what they care about. So now it says 2 students plan to investigate this equilibrium shown below. So we've got COCl4, which is blue, and plus H2O, and it goes to 6 and whatever, right? So the students are supplied with the equilibrium mixture in this at room temperature. One student heats 20 centimeters cubed of this to 50. The other one heats 20 centimeters cubed to 90. So the students use colorimetry to observe the color of the equilibrium mixture changes over time. The colorimeter is set up so the greater the absorbance, the greater the concentration of COH2O6. So in this sense, essentially, that's the COH2O6 2 plus concentration. The initial absorbance is set to 0. It's done every 30 seconds. They plot the graph of the results. So it says use the graph and the relevant chemical theory to answer the following, including all reasonings. Explain the different initial rates of 50 and 90, and then predict the signs of the delta H for the forward reaction in this equilibrium. So number one is that, well, let's talk about this. Explain the difference in the initial rates. This is the absorbance over time. So as time goes on, you can see that the absorbance increases and then it increases. What I like to do is I always look at things line by line. So this dotted line, its absorbance increases, and starts to level off, meaning its concentration of CO increases and levels off. Whereas here, it increases and also levels off. However, if we compare the two, this one's increasing a bit faster, but then levels off earlier, and lower, whereas this keeps going for a little longer. So initial rates is all about how fast things are changing at the start. So if I did this, that's going really fast because a tiny increase in the time is a massive jump here. The gradient can tell you the steepness. The gradient tells you the steepness. The steepness can tell you the rate. So in this case, at 90 degrees Celsius, it says explain the difference. We need to say what the difference is. Well, the 90 degrees is that the initial rate is higher. Now you need to think why. Any reaction can only happen if you've got two things met. They collide in the right orientation and they have the activation energy. If they don't have these two things, then it won't happen no matter what. Even if you have the activation energy and they're here and here, they will not react. Reactions are all about things smacking into each other and then they react. Even if they collide without the activation energy, they can still collide and nothing happens. So just make sure you really remember this and drill it into your head. With any reaction happening, it has to have those two things. So in that case, if it's going faster, these two things must be optimized. They must be getting better. So if the initial rate's higher, that must mean that we have higher temperature gives you more kinetic energy, so they're moving around quicker. So there's more collisions leading to reactions in a given time. Because remember, we're talking about rates. It can't be just more collisions as a whole, because what if it's like over years? It's in a given time, but also more particles have more than the activation energy to react. So there's that as well. Now, we need to figure out what the sign for delta H is in this forward reaction. So the forward reaction shows that you're going from COCl to COH2O6. So if the absorbance is higher, what it means is we're getting more of this. So when we have a lower temperature, it seems that this goes higher than if we increase the temperature. If I compare 90 to 50, so let's pretend we did it at 90, then we switched it to 50. The change that we've made to the equilibrium is that we've decreased the temperature from 90 to 50. But the equilibrium wants to counteract the change. The equilibrium wants to increase the temperature. And how does it do that? Well, in this case, it's done it by making more COH2O6 And in our example, we can see that is on this side, so the equilibrium has shifted that way. So it's shifted to the right. So if that means that this shifting to the right increases the temperature, that must mean that it is an exothermic reaction. And there you go. So it must mean that the forward reaction delta H is negative because decreasing the temperature from 50 to, decreasing the temperature, I should say. Decreasing the temperature from 50 to 90 increases the concentration of COH2O6 2+. You can do it the other way, where you can say, the temperature's increased, the equilibrium wants to try and decrease the temperature, so you actually get less H2O6. It's actually shifted to the left. It's the same principle, either's fine, but it's asking you about the forward reaction. So the students investigate how addition of silver nitrate aqueous affects the equilibrium position there. The graph shows the change in the equilibrium concentration of COCl4, 2 minus Cl minus, and COH2O6 after adding AgNO3. The AgNO3 added is at the time t. So they told you that at this time here, where that line is, they've added the aqueous silver nitrate. Explain why Cl minus concentration drops sharply at this point. So just look at this equilibrium here. We're adding AgNO3. You need to look at this and say, well, realistically, what's it going to react with? It's going to go for these chloride ions, and it's going to make silver chloride, which is that nice, lovely precipitate we love and enjoy. So what happens is that AgNO3 aqueous is what I meant to say, reacts with Cl minus to form AgCl. Even without looking at that, I can, get that answer. But yeah, it's told you here, it drops sharply, so you need to think, well, what's that going to react with? So it says, explain the changes in the concentration of COCl4 minus in this and the change at the time t. So you can see it drops sharply here, right? Fine. If that drops, remember that so decreasing Cl minus means that the equilibrium, because that's the change you make, shifts to try and increase the Cl minus. Therefore, the equilibrium shifts to the right. So so as a result, if it's shifting to the right, we're going to get less of this, we're going to get less of that, and we're going to get more of this. So therefore, we get less COCl4 minus and increased COH2O6 2+, which is exactly what we see here. You can see it drops and then that goes up. And then So we've talked about the COCl4 and the COH2O6, right? But we haven't discussed the Cl minus. Why has it dropped so sharply? You can see that this drops by about like one line. That's one. But that's 1, 2, 3, 4, 5, like 5-ish. If you look here, there's 1 mole of that, 6 moles of that, 1 mole of that, and then 4 moles of that. So each mole of this is going to give you 4 moles of this. So if I've added AgNO3, then that's going to drop sharply. So then this is going to dissociate to try and shove out as many of them as it possibly can. So what happens is, if we look at its very bottommost bit, it's going up by 1, 2, 3, 4, because this is after the time t, remember? This is going after time t, that goes down by 1, that goes up by 1. So you can see that the increase in Cl minus is 4 times these changes here, and that makes sense because there's 1 to 4. 1 mole of these reacts to give you 4 of them. So if one of those reacts with this, that goes down by whatever, this will go up by 4 times as many. So then the other thing is that Cl minus increase is 4 times the COCl42 minus, or the other one. There you go. This question is about energy changes. A student plans to determine the enthalpy change of hydration of calcium ions, and they find this information from some data tables. So they've got the lattice enthalpy of calcium chloride. So whenever you have questions on enthalpy changes, my honest opinion is that if you're complaining about having to learn these definitions, you're learning the topic wrong and you don't know what you're doing, because these definitions are crucial in all these questions and should be free marks, to be honest. So if you're doing an enthalpy changes question, you must, no excuses, do a Hess's law or Born-Haber cycle. There's no other way around it. You can do whatever you want to try and do other weird ways. It just don't work. So ignore any BS you hear out there. The only way to do these is Hess's law or Born-Haber cycles, end of. If you're finding that you have to complain about learning the definitions, then you're doing it wrong, because this whole topic hinges on you knowing those definitions and doing them and using them right. So I'll show you what I mean. In this table below, they've shown you the lattice enthalpy of calcium chloride. So lattice enthalpy, its definition, is the enthalpy change where you form 1 mole of a solid ionic compound from its gaseous ions under standard conditions. So that means we're going to go from gaseous ions to a solid ionic lattice. Enthalpy change of hydration is one where 1 mole of gaseous ions becomes hydrogens, blah, 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 whatever, right? The definition. So I know I'm going to start with gaseous ions, and then I'm going to form aqueous ions. And then, what have they done? They found the enthalpy of solution of calcium chloride. So the enthalpy of solution is where you get 1 mole of solid ionic lattice and dissolve it, blah, 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 and you get aqueous ions. So we know it's solid ionic lattice to aqueous ions. The reason this is important, because this will help you shape the cycle that you end up making. So then the student does all of this stuff, blah, 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 and they measure the temperature changes, and then what they're doing is they're trying to find the enthalpy change of solution. So now what we're going to do is we're going to use their numbers to calculate the enthalpy change of solution and then make a cycle with that. So in this case, because it's calorimetry, we're measuring temperature changes and stuff, we're going to use Q equals MC delta T. So delta T is the temperature change, which we can work out as this minus this. So the temperature change is going to be 18.5 degrees, because it's this final temperature minus the first. So that's delta T sorted. Then C, they've told you in the question to assume that C is the same as the water, so it's going to be 4.18. And then it's told you, then we need to figure out M. M is not the mass of the stuff you use. M is the mass that's either of the thing that's either being heated or lost heat, right? So it's the water, essentially, that you would have, or a solution that's getting warmer or colder. So in this case, they've told you that there's a solution here, and they've told you to assume that it has the same density as water. Density of water is 1 centimeter cubed, so it's 1 centimeter cubed is 1 gram. So 1 gram per centimeter cubed. So every centimeter cubed is 1 gram. So in this case, we can see that the mass of the solution here is actually, well, we don't even need to use that because they've told you that the mass is here. But if they told you a volume, then you would know that the volume has to be 1 centimeter cubed, 1 gram, because it's the same as water. So in this case, the final solution is going to be these two subtracted, which is 106.6 grams. So that means that Q is going to equal 106.6 times 4.18 times 18.5, which gives you 8243.38 joules. But we want it in kilojoules because it's in kilojoules per mole. All enthalpy changes are that. So that means we're going to divide it by 1,000, so 8.2434. Let's go with that, kilojoules. Right, but that's not done yet. We actually need to find out what the enthalpy solution is of the CaCl2, because the reason we use per moles is because it's standard. It means every single 1 mole of that will do it. In this case, we don't know how many moles of this we have, so we're going to have to work that out, because if we have like 2 moles, then it would be double the enthalpy change you should have. So then what we need to do is we need to find the moles of the CaCl2, which is going to be its mass over its MR. So we know that this is here, and here, and then this is without it. So these two the difference between these two is going to be its mass. So the mass of this thing is going to be 9.28, and its MR is 111.1. So that means you get 0.0835 moles. So therefore, delta H's solution is going to equal the energy released, so 8.2434. That's for this many moles of that, it releases that much energy, so 0.0835. So then you're going to get an enthalpy change of 98.7 kilojoules per mole. Now, because it's a temperature increase, it's going to be exothermic negative. Now we need to construct the cycle. Whenever you're constructing a cycle, the definitions will tell you what you start and finish with. Because we're dealing with the enthalpy of solution here as our overall equation, I'm going to write that out. So we start off with a solid ionic lattice, and it eventually becomes Ca2 plus, because it's and it's 2Cl minus, which is its aqueous ions. So that is your enthalpy of solution. Each arrow in a cycle is an enthalpy change. Hess's and Born Haber's. So then we need to look. We have a solid ionic lattice here, and they've given us this in the table. Do anything, link. Well, solid ionic lattice, right? So these must be the same thing being presented, and we can see gaseous ions. So that means that this probably links to gaseous ions like Ca2 plus gaseous plus 2Cl minus gaseous. So then you look at it again, this is lattice enthalpy of calcium chloride, which is where you're going from gaseous ions to 1 mole of a solid ionic lattice. So that means that this arrow is going to go from the gaseous ions, like we've written here, to the solid ionic lattice, so upwards like that. And that's going to be your lattice enthalpy. Then, the enthalpy of hydration, they've told us, is where you go from gaseous ions to aqueous ions. You can see that we've got gaseous ions here and aqueous ions up there. So for chloride, it's going to go up like that, and that is the enthalpy of hydration for the chloride ions. However, the question wants us to find the enthalpy of hydration of the calcium ions, so we've actually got another arrow going up here, and I'm going to call that X. So then, remember that Hess's law says if you start and finish at the same point, no matter how you get there, the enthalpy change is the same. So we're starting here, we're finishing here, that enthalpy change is minus 98.7, or the enthalpy of solution. So it doesn't matter if we went all the way around here, it's still going to equal that. So therefore, we can say that this overall reaction, minus 98.7 equals, so the lattice enthalpy, remember, is this to this, but we're going the opposite way now. So it's going to be the other way around. So it's going to be 2, 2, 2, 3, right? And then we're following this. It's going to be plus X and then plus enthalpy of hydration of chlorine. But because remember the definition says 1 mole of gaseous ions to aqueous, but we've got 2, it's going to be double that. So it's going to be plus 2 minus 378. So therefore, X is going to equal minus 98.7 minus 2223 minus 2 lots of minus 378. If we do that, we should get minus 1565.7, which is roughly minus 1566 kilojoules per mole. Done and dusted. That's how you do them every single time. So now it says internal combustion engines have historically used fuels obtained from crude oil as a source of power. The environmental effects of fossil fuels can be reduced by blending petrol with biofuels such as ethanol. A fuel being developed is using a 1-to-1 molar ratio of octane and ethanol. Write an equation to show the complete combustion of this fuel. Again, it's told you in the question everything. So write down what you know straight away whenever you're writing an equation. So they've told you that it is octane. So octane is an alkane, CnH2n plus 2. So it's going to be C18H2n is 16 plus 2, 18. And then plus ethanol, which is going to be C2H5OH, right? Now they've told you that we've completely combusted this. It's going to be plus O2, some amount of it. And when we combust these, we're going to make CO2 plus H2O. So then all we got to do is we've got to balance these out. So we've got 8 carbons plus another 2 here. So we've got 10 CO2s here. And then how many hydrogens have we got? 18 plus another 6, remember? So 18 plus 6 is 24. So we're going to have 12 H2O. So then we're left with C2H5OH. So that's what? 32. But we've already got 1 oxygen here. So that means we've got 31 left. So that's 31 over 2. That's 15 and a half. Next, it says calculate the energy released in kilojoules by the complete combustion of 8 kilograms of this fuel, and they've told you the enthalpy of combustion is this, and the enthalpy of combustion is that. So the MR of the octane is going to be 114, and then the MR of the C2H5OH is 46. This fuel is a mixture of these two in equal amounts, so you can consider the MR of the whole thing, the mixture, to be those two added together, which is 160 grams per mole. Right? So then what we can do is we can work out the moles of each of these two things together. So what that means is if we do the moles of this whole thing, the mixture, is going to equal 8,000 divided by 160. And if you do that, you get 50 moles. So that means that you've got 1-to-1, 50, right? So that means you have 50 moles of each thing. The way I like to think of it is that we've got 50 moles of fuel, which is the same as these things, right? So that means we have 50 moles of each of these as well, based on the chemical equation. So what we do now have is we know that our octane moles are going to be 50, and we know that the octane of ethanol is also going to be 50, because logically speaking, we could just put that as one big chunk, and that could still be 1. So it's just separating out into its two things, which is still going to be 1 and 1, if that makes sense. So here, that's how many moles we have. Now this tells us that we have minus 5470 kilojoules for every single mole of this we have released. So because we have 50, the energy released, and for this one as well, is going to equal its moles 50 times, and then their enthalpy changes minus 5470, and then that one's what, minus 1367. If we do that, we should get, let's see what numbers we get. 50 times minus 5470 is minus 273500, and then we have 50 times minus 1367, which is minus 68350. So then therefore the total energy released is going to be those two added together. So if I do that, we get minus 341850 kilojoules. Well, in this case, I just want the energy released. Remember, that's a negative thing because it's exothermic, so it's just you can just write 341850. There you go. So now it says, a student carries out an investigation on vitamin C. Here, the structure of vitamin C is shown, and it's an optical isomer. What is the total number of optical isomers that you can have with this vitamin C? So we need to look at how many chiral carbons we have. No chiral carbon here, so you're out. No chiral carbon here, nope. Yes, so we've got one there. And then that's not a chiral carbon either because it's got a double bond there, so that one's out. Here, we've got 1, 2, 3, and then a hydrogen, so there's 2. No, there's a chiral carbon there. No, there isn't because there's an HH there, so no chiral carbon. So we've only got 2 chirals. So each chiral carbon can have 2 optical isomers, so because you've got your 2 enantiomers. So because there's 2 of them, you're going to have 2 times that, which is 4. Vitamin C is extremely soluble in water. This means it can be removed rapidly from the body. Vitamin C as an ester is available. Vitamin C ester is available in tablet form, and a less soluble source of vitamin C. It stays in the body for longer. Suggest why it's extremely soluble in water. So you need to look at this and think what's going on here. Well, the only thing you can see in this structure is that it's got this. It's got a double bond. It's got this. But you can see this, and this. And you should then realize, oh, it's got OH, it's hydrogen bonding. So suggest why it has many OH groups. So lots of hydrogen bonds. It's the only reason I can think of an explanation for it, and you can as well. So there it is. A vitamin C ester tablet contains an ester with this molecular formula. This ester can be prepared by reacting vitamin C with a long-chain carboxylic acid. This in the presence of an acid catalyst. Vitamin C and the long-chain carboxylic acid react in a 1-to-1 ratio. Determine X and Y in the formula of this. So they very nicely told you that. Okay, so the question's it's told you that the question has said vitamin C will react in a 1-to-1 ratio with that thing there. So C6, H8, O6, will react in a 1-to-1 ratio. It's a mysterious carbon thing here, long-chain carboxylic acid, CXHYCOOH, and it then makes an ester with C22H838O7. So start by always writing what you definitely know from the question. Now, because this is an esterification reaction, it's condensation, you're going to be putting out some H2Os as well. You need to figure out how many H2Os have been messed with. So off the bat, you can see that it's reacting with a long-chain carboxylic acid in a 1-to-1 ratio. So that means that, well, if that's C22 and we started with C6, we've got CX and some number and another carbon here. So that means 22 minus 6 is going to equal CX plus the other carbon there, 1. So 22 minus 6 is what, 16 equals CX plus 1. So CX is going to be 15. So the X, we already know, is 15. Well done. Woohoo. Now we need to figure out what the H is. The problem is with these H's is that some of them come out as waters. So we've got here, we need to figure out how many waters we've lost and whatever, then we can figure the rest out, right? So you should be able to recognize that's an alcohol, that's an alcohol, that's an alcohol, that's an alcohol, right? So off the bat, you should be able to tell that. And then we need to figure out what part of this is a carboxylic acid. So this is a carboxylic acid, remember, where it's told you it's a COOH. We now end up with C22H38O7. So we'll look at the oxygens. We're going from an O6 to an O7. So that means that only one of those alcohol groups will have reacted. And that also makes sense as well, because these alcohol, and they've told you it's a 1-to-1 ratio. So we know for a fact that we have got one water coming out of this, because it's a 1-to-1 ratio, one esterification thing. So that means if we've got one H2O left, then that means that 8 plus Y plus 1, because there's 1 here, equals 38 plus 2. So that means that 9 plus Y equals 40, so Y must equal 31. And there you go, that's how we do it. So there. So now it says vitamin C is a weak acid, Ka, which is often referred to as ascorbic acid. In aqueous solution, vitamin C donates a proton to water. Add curly arrows to suggest the mechanism of this process. So you can see we've got an H2O. Compare them side by side. What has changed? Like, what can you see is obvious? Well, that's got an H now versus that. So it's definitely, those electrons have been given to an H+. What about this? What's changed? Well, the double bond is gone here, and now we've got an O-, and then we can see that this has become a double bond O. So straight away, I can see that this has become a double bond to a single bond, and this has gained electrons. So what's happened is those electrons must have broken, like that bond must have broken like that. Now, this has become a double bond O, and there's no H left. So that's probably where the H has come from. So we don't draw arrows going from the H to here, because that's implying that the H is giving electrons to the oxygen, which is not happening. It's the other way around, because it's donating the proton to water. So this O makes a bond with the H like that, curly arrow there. That deals with the O bit gone. There's no H there now. So that's fine. We're happy with this part. We're happy with that part. However, this double bond is now here. So what's happened here is this hydrogen's got too many bonds. It's like, I don't like this. So what it must have done in order to fit here is it must have given electrons to this bond like so, like that. That's happy with the double bond scenario. But the issue is here, double bond's there, but there's not one here. And that makes sense because this now has too many bonds if there's a double bond there. That carbon there's got 5 instead of 4. So what this must have done is it must have drawn an arrow pointing here to give you a double bond there instead, and that's that. So remember that. Think of it in terms of electron pair movements, these double-headed arrows, and you'll be fine. And just compare side by side. And then no matter what mechanism in the world you get, you can do it. Now it says the student dissolves this much vitamin C and makes the solution into a volumetric flask. Calculate the pH of this solution C. So whenever you're doing an acid-base question, you need to think, is it a strong acid or is it a weak acid? Is it a strong base or it's a weak base? If it's a strong acid, you can assume that the concentration of the acid is the same as the H+, unless it's diprotic, because the acid fully dissociates. Now here it's a weak acid, right? So it means it only partially dissociates. Now, if it partially dissociates, you're going to have to use Ka. Now the options are Ka equals H+ squared over HA, and then you've got, or Ka equals H plus A minus over HA. Now, you need to look at this at a very face value superficial level. H plus is the number of protons. You're going to eventually use that to find the H plus, the pH. That is the concentration of the acid. So A minus, what's that? That is the moles of the salt, generally speaking. So if you just remember that as moles of salt, remember that anything with an OH minus is base. If you see that, that's moles of base. Then it makes sense, because this, well, there's no A minus or any salt mentioned here, so we're not going to use that. And that's for a buffer, really, mainly. But if you remember that A minus is salt, then you're going to be fine. So in this case, H plus equals Ka times HA, and the square root of that. H plus is going to equal the square root of 7.94 times 10 to the minus 5 times the concentration, which we need to figure out. So concentration is going to be C equals N over V, which is 0.150 over 250 over 1,000. So then that's the concentration, so 0.6, which gives you 6.90 times 10 to the minus 3 mole dm minus 3. So then to find the pH, it's just a negative log to the base 10 of that H plus. We get 2.16. Remember that it has to be 2 decimal places, and there you go. So now it says the label on a carton of an orange juice contains the mass of vitamin C in a typical serving of 100 centimeters cubed. So it's the volume we're going to be using. A student carries an investigation to find out the vitamin C content in the orange juice, and it can be oxidized by iodine. So C6H8O6 gets oxidized to this plus 2I minus plus 2H plus. Fine. The student dilutes this much orange juice with water to make that in a volumetric flask. So they've got OJ, they've got 150 centimeters cubed, or 1 serving of it. And they've added water to 250 centimeters cubed. Then what they did is they titrated this volume with this. So don't just, when you're doing these questions, look at this thing sentence by sentence, make a picture in your head of what's going on, and make sure you know what volume or this or that belongs to what, and then your life is a lot easier. So titrates 25 centimeters cubed of volume of this solution. Don't just say that, like, what is that? So they took 25 centimeters cubed of this stuff with the orange juice and the stuff mixed in, right? And they titrated it with I2. So don't say titrated, just say reacted it with. And then how much? Well, they used what? This concentration, 9.60 times 10 to the minus 4 concentration, and the volume of it was 22.5. And this was what? I2. It says determine the mass of the vitamin C in a 150 centimeter cube sample. So they want the mass of that. So now you can work backwards, because now you know, well, the vitamin C and the I2 react, and we now know its concentration and volume. So the moles of the I2, so whenever you're doing this, don't blindly work things out. Be able to justify why you've done it. So what am I going to do with this step straight away? So the reason I'm working this out is because then I can find the moles of the vitamin C in the 25 centimeter cubed sample, wherever it is here, and then we can know that that's going to be times 10 to get back up to here. All the vitamin C in here must have come from the orange juice, and then I can do the mass from there. So that's why you need to be able to justify every single step. So the moles of the I2 is going to be its concentration times volume, so 22.5 over 1,000 times its concentration, which is 9.6 times 10 to the minus 4, which is 2.16 times 10 to the minus 5 moles. We know that, therefore, the moles of the vitamin C in 25 centimeters cubed is going to equal the same because they're in a 1-to-1 ratio. But then in the 250 centimeters cubed sample, because that's what they dissolved it in, and this is where people fumble because they're like, oh my God, 150, 250, you don't. It's going to be your answer times 10, which is going to be 2.16 times 10 to the minus 4 moles. Now, we know that this many moles has come from the OJ, which is 150 centimeters cubed. There's no other reason why there would be any vitamin C in there. So that must mean that we can work out the mass of the vitamin C, because all of that must be the vitamin C in this orange juice solution. So 2.16 times 10 to the minus 4 moles times the MR of the vitamin C, which is 176, will give you 0.038016 grams, but the question wants it in milligrams, and this, remember, is from the 150 centimeters cubed sample, so it's going to be 38 milligrams divided by 1,000. So if you just follow the steps like that, this question was what, like 4 marks? But it looks like huge amounts of work needs doing. I only did 1, 2, 3, 4 lines. There you go. I hope that helps. Thank you very much. Please like, share, and subscribe. You know the drill, and share it with all your friends as well.